Okay, so what if I told you there's a single, universal law that governs pretty much everything? We're talking the weather, the economy, even artificial intelligence. Well, a brand new scientific paper is proposing exactly that. And at its heart is an idea you'd literally never expect to find in a physics paper: compassion.
So get this. This is the final sentence of the paper, and it's an absolute bombshell. The authors are basically suggesting that compassion isn't just, a feeling or a moral choice we make. They're saying it's a fundamental property of the universe, as real and as necessary as gravity.
So yeah, could compassion just be a law of physics? That's the huge question we're going to tackle in this explainer. How on earth did a team of physicists and data scientists even get to a conclusion like this? Well, to understand their new law, we first have to look at the old way of thinking they're trying to completely replace.
You see, for the longest time, the way we thought about stability is that it's this constant struggle, right? A never-ending fight against chaos and decay. A reactive battle just to keep things from flying apart.
The classical view is all about being reactive. You wait for a problem to pop up, and then you scramble to fix it. But this new law, it proposes something totally different. It's proactive. It's not about fighting chaos, it's about actively preserving the system structure before any problems can even start.
Here's a simple way to picture it. The old view is like you're standing on a beach, just getting constantly knocked over by waves. The new view is about seeing that wave coming, understanding its shape and its power, and then using its own energy to stay balanced and ride it. It's all about foresight, not just brute force. So what is this structure that stable systems are supposedly trying to protect?
And that leads us to the absolute core concept of this entire paper. The secret ingredient that really unlocks this whole new understanding of stability is a property that they call coherence. Now, I know that sounds super complicated, but the idea is actually pretty intuitive. Coherence is just a way to measure how much predictable structure a system has. Think of it as the exact opposite of pure randomness. And here's the crucial part. According to this new law, the main goal of any stable system isn't just to save energy. It's to preserve its own predictable patterns, its coherence.
A flock of birds is a perfect example of this. A single bird's path might look totally random, but the flock as a whole, it moves like this single, beautiful, structured thing. You can pretty much predict its general direction. That structured predictability is coherence. So how do systems actually do this? How do they protect their coherence?
Okay, so this is where things get really cool. The paper argues that to conserve coherence, a system has to be able to anticipate the future. It needs to have some kind of foresight engine built in.
To test this whole idea, the researchers actually built a special AI. Let's just call it the predictive controller. Its one and only job is to look ahead, predict any threats to the system's coherence, and then act early to steer everything back toward a stable, predictable path.
So how does this thing actually work? Well, the process is pretty logical. First, the AI senses what's happening in the system right now. Then, it forecasts a bunch of potential futures to see what could go wrong. Now, this is the key part. It then chooses the path that leads to the most predictable, most stable outcome. And finally, it acts now to prevent that future problem from ever happening. It's surfing the wave, remember? Not getting smashed by it.
Okay, it's a fascinating theory. I mean, it's a great idea on paper, but does it actually work? Well, this is where the paper gets really interesting. The researchers tested their predictive controller on an incredible range of completely different systems. And just look at the diversity here. We're talking everything from the pure physics of turbulent fluids to the behavior of other AIs, all the way to simulations of economic markets and complex ecological cycles. The big question was, does this one single principle, conserving coherence through foresight, hold up everywhere? The results were staggering.
Let's just fire through some of the results. In a simulation of turbulent fluid, which is like the classic model of pure chaos, the predictive controller cut that turbulence by over 22%. To put that into perspective, that's like being able to calm a stormy river just by predicting where the whirlpools are going to form and stopping them. It literally smoothed out the flow of chaos.
And what about that structured predictability, that coherence we talked about? Well, get this. Across all of these completely different systems, the loss of coherence was kept to less than 1%. That is insane. It means these systems maintain their predictable structure with unbelievable efficiency, whether they were modeling economies or ecosystems. And maybe the most mind-blowing result of all, the overall resilience of every single system they tested at least doubled. That means they became twice as good at handling unexpected shocks and disturbances from the outside world, all because they were proactively looking ahead instead of just reactively fighting chaos.
So, okay, let's bring this all back home and connect it to that wild opening quote. How does all of this, coherence, foresight, and stability, actually add up to compassion being a fundamental law of physics?
All right, let's just build the final argument piece by piece. The experiments clearly show that for any system to be stable,
It absolutely has to preserve its own internal structure and predictability, its coherence, right? That's job number one. And the only way to do that effectively is by looking ahead and acting on future risks, not just the problems you see right now. The system has to choose the path that is safest and most predictable for the whole system. And the paper gives us a name, ethical foresight, because it's about making choices that benefit the future of the entire system. And this right here, brings us to their radical redefinition. In the language of this new law, compassion is this physical process. It's the proactive conservation of coherence. It's the act of seeing a future threat to the system's very structure and acting early to prevent it. It is foresight in action for the good of the whole.
So, at the end of the day, it all boils down to this one elegant equation from the paper. That little triple bar sign means is defined as or is identical to. What they're showing is that mathematically, in any stable system, a state of regularity, the act of conserving coherence, and the act of ethical foresight are all just different ways of describing the exact same thing. So what does this all mean for us, for you and me? This paper suggests that for any system, whether it's a star, a single cell, an AI, or even our own societies, the path of foresight, of caring for the future integrity of the whole system, isn't just a nice moral idea. It might be a physical imperative, hardwired into the fabric of reality itself. What if the most compassionate choice is also, by the very laws of physics, the most stable and resilient one?
Welcome to the deep dive. So how do you stabilize a system? I mean, if you're a physicist, maybe you look at energy. An economist, you're probably thinking incentives.
Right, or AI, maybe error boundaries.
Exactly. But what if all these, really different problems, turbulent water, unstable markets, what if they're all just different sides of the same coin, governed by maybe one single underlying principle?
That's a pretty radical idea.
It is. And today we're taking a massive intellectual leap, really. We're diving into this paper that's making some serious waves. It's called the Universal Stability Law v3.0, Predictive Coherence Control and Ethical Foresight.
Published by the Skylar Fiction Coherence Lab. Quite a name.
Huh, yeah, bit dramatic. But the ideas are serious. So our mission for you today, our goal is to pull out this unifying principle they're proposing, one that supposedly connects fluid dynamics, predictive AI models, and, believe it or not, the concept of compassion.
It sounds almost too broad to be true.
It does. The core thesis we're testing here is that stability isn't about reacting to chaos after it happens. It's achieved through the proactive conservation of coherence when there's delayed feedback in the system.
Okay, that's a mouthful. Let's break it down. Proactive conservation of coherence.
Yeah, coherence. That seems to be the key. Let's get started there.
Right. So what's fascinating right off the bat is that they needed a new foundational measure to even try this kind of universal thing. They introduced coherence, and they treat it as an information thermodynamic quantity.
Okay, information thermodynamics. So not just order in the simple sense.
No, it's more specific. Think of it as structured predictability. Imagine like a perfectly woven piece of fabric. Coherence is the integrity of that weave.
Mm-hmm.
If threads start pulling out randomly, the structure, the predictability of the pattern gets lost. That happens even before the fabric actually rips apart.
Okay, I think I get that. It's the reliable structure.
Exactly. And they're claiming that structured predictability is the thing that's conserved in any stable system. So instability isn't just things breaking down, it's when that coherence gets shuffled around so fast, the system basically loses track of where the structure went. It can't predict its own state anymore.
That makes intuitive sense. So if classical physics is often about chasing energy equilibrium, this sounds like it's chasing predictability equilibrium. Is that fair?
That's a great way to put it, yeah.
But how do they nail that down mathematically? What's the actual rule here?
Well, they ground it in what they call the Information Coherence Regularity Theorem, the ICRT. This is really the engine of the whole paper.
Yeah.
It basically says that the system's instability measure, they use the Lyapunov cost, Lawler dollars, so the rate of change of that cost, DLDT2, will be non-increasing, meaning the system is stable. If and only if the change in the total coherence, DLT time is basically zero. DLTT is approximately zero.
Wow, okay. So mathematically speaking, you can just hold the line on this structured predictability. Stability is guaranteed. Conserving the structure is conserving resilience.
That's the core claim. That's the foundational theorem. Now, of course, they had to show that a control system built on this idea could actually work and work across different kinds of systems.
Right, the universality claim. Okay, let's unpack the methods then. How did they start testing something this big? Phase I, you mentioned, the physical foundation.
They started with arguably one of the toughest problems in classical physics, the incompressible Navier-Stokes equations. These describe fluid flow, turbulence, chaos.
The hard stuff.
Exactly. And to keep the math clean, they ran their simulations on a torus, PT3 to 3Lers.
A torus, right? That's like a donut shape. Why the donut? Just quickly for listeners.
It's a common trick in physics. A torus has no edges or boundaries, so mathematically it isolates the fluid flow. You don't get weird effects from walls or containers. You're just studying the pure internal dynamics of the turbulence itself.
Got it. Pure turbulence.
But here's the twist. They augmented the standard equations. They added a field representing this coherence concept. So every little point in the simulated fluid has a coherent score tracking its local predictability.
Okay. Simulating fluid flow.
Yeah.
But with this extra layer of predictability scores everywhere. Now, this is where the language got, well, really interesting. They introduced a controller, the LRC, Lagrangian relaxation controller, and it includes something called the compassion gradient. Hold on. Are they just giving a fancy name to a damping mechanism? Like compassion is just slowing things down?
That's a critical question, isn't it? And it goes right to the heart of their argument. Mechanically, the LRC's job is pretty straightforward. It adjusts two parameters, alpha and beta, to keep the total system coherence, CT2, constant.
Okay, alpha and beta. Tell me about alpha first, the compassion one.
Right. So alpha is the parameter they explicitly say couples these compassion gradients to the fluid's velocity. Think of it as a force that actively nudges the flow in ways that maintain the structural integrity, the local coherence to it.
So if a region starts losing its structure?
Alpha generates a force to counteract that, to restore the coherence there.
Yeah.
Beta, the other parameter, is simpler. It just represents the energy cost associated with doing that restoration.
Okay.
Now, the authors argue that because this alpha-driven force proactively works to maintain the integrity of all parts of the system, anticipating and preventing breakdown rather than just reacting to it, that behavior is computationally equivalent to compassion, an active concern for the well-being or integrity of others within the system.
Okay, I see the distinction now. It's not just damping. It's an active, structure-preserving force. That makes it different. So that's phase one, reactive control based on current coherence. But the paper is V3.0. It's about Foresight. That must be phase two.
Exactly. Phase two is where they introduce the predictive LRC, the PLRC. This changes everything. It incorporates a predictive model.
An AI model.
A very sophisticated one, yes. A Fourier neural operator, version 2 FNOV2. It acts as a surrogate model. Its job is to look at the current state and forecast the future instability cost. The likely Lyapunov cost lowers at some point 2 plus USO in the future.
So it's literally predicting where and when the turbulence is likely to spike, or where the structure might start to fail before it actually happens.
Precisely. And this is the key step that enables what they call the ethical control loop. The system uses this forecast in a model predictive control, or MPC, framework. But here's the crucial part. It doesn't just aim to minimize the predicted average cost.
What does it minimize then?
It minimizes a different combined cost function, do dollars. This function is the expected future cost plus a penalty term based on the variance of that prediction. Do dollars plus lambda var.
Wait, how are that? The variance of the prediction itself. So they're penalizing uncertainty.
Yay. Hugely penalizing it. That lambda term, lambda, can be set to heavily weight the variance. So the system isn't just trying to find the path with the lowest predicted average instability. It's trying to find the path where it's most confident about the outcome.
Ah, okay. So it actively avoids paths where the AI model says, well, the average outcome might be good, but I'm really not sure. It could be great or it could be disastrous.
Exactly. That high penalty for predictive variance is what they term ethical restraint. The system is mathematically programmed to prefer high-confidence, low-risk trajectories. It will choose a slightly higher but certain cost over a potentially lower but highly uncertain cost. It's inherently risk-averse about the future.
And how do they estimate that uncertainty, the variance?
They use a standard technique in machine learning called a Monte Carlo dropout. Basically, they run the FNO prediction multiple times with slight variations and see how much the results scatter. High scatter means high variance, high uncertainty.
So the math itself is designed to punish recklessness and demand predictability. And that computational preference for stable, certain futures is what they're linking to prudence and ultimately to ethics.
That's the core of the argument. Prudence isn't some add-on moral choice here. It's presented as the most computationally effective strategy for maintaining long-term structural integrity when dealing with prediction.
That's quite a claim. But okay, if the universal law, it can't just be about fancy fluid simulations. Phase 3 must be about showing this works elsewhere, right? The cross-domain test. How did they take this PLRC controller and apply it to, I don't know, social systems, economic behavior?
They did exactly that. They set up generic complex adaptive system analogs, CAS models. The clever part is how they mapped the variables. The underlying mathematical structure of the controller remained identical. They just relabeled what the variables represented.
Okay, give us some examples. How does fluid velocity translate to something social?
All right, so velocity vector in the fluid model was mapped to things like agent action flow in a social simulation, sort of the collective momentum or behavioral trends of agents.
Makes sense. What about the crucial variable coherence signaling?
This is fascinating. In the social analogs, SIDM was directly mapped to things like trust density or cooperation density.
Wow. So the structural predictability, the integrity of a social system is literally equated with the level of trust and cooperation within it. If trust erodes, coherence drops, and the system heads towards instability.
That's the model. And they tested this mapping on systems representing quite different things. Internal cognitive processes like neural network parameter drift over time, models of economic transaction rates, and even ecological models looking at population dynamics and feedback loops.
Same controller, same math, just different interpretations of $1 dollar.
Precise.
All right, this is the moment of truth then. What did the results show? Did this PLRC controller, guided by conserving coherence and avoiding uncertainty, actually stabilize these completely different kinds of systems? Give us the hard numbers.
The results they report are remarkably consistent across the board. The stabilization was definitive. First off, the core variable, coherence itself. They maintained incredibly tight control, reporting sub 1% coherence drift across all domains. The maximum error, epsilon COs, was consistently below 1.2%.
Sub 1.2% drift in coherence. That's incredibly stable.
Yeah.
If the system's structured predictability barely wavers, it essentially never gets chaotic, does it?
Pretty much. And it wasn't just about maintaining the status quo. The controller actively improved regularity. Back in the physical domain, the fluid dynamics, they measured a 22.5% reduction in entropy.
Entropy, remind us.
It's a technical measure of the intensity of rotational motion in the fluid, essentially how much chaotic swirling is going on. Reducing it by over 20% is significant smoothing.
Okay, smoother flow. What's the bigger implication of that, though?
The really big one, theoretically, was the complete elimination of finite time singularities in the physical model.
Singularities, those are the points where the standard math breaks down, right? Predicts infinite energy or something impossible.
Exactly. They're theoretical points of catastrophic failure in the standard models. The coherence law, as implemented by the PLRC, apparently prevented these from ever forming in their simulations. It implies the system doesn't just manage turbulence, it fundamentally restructures itself to avoid these theoretical collapse points.
Okay, eliminating the mathematical possibility of chaos. That's not just an improvement. That feels like a different kind of physics, almost. Did this improved stability hold up in the other domains, too?
Yes. Across all the CAS analogs, social, economic, cognitive, the stability margins were reported as being at least double the baseline. So these systems became twice as resilient to shocks compared to the uncontrolled versions.
Twice as resilient. And how did it achieve that? Was it just reacting faster?
No, and this is key. Because it was predictive, it almost entirely eliminated reactive damping. The controller wasn't waiting for coherence to drop and then fixing it. It was acting on anticipated drops in coherence, proactively steering the system away from futures where the predictor was uncertain or predicted instability. It acted before the problem even manifested.
Right, the Foresight. It prevents the fire instead of just putting it out. Okay, the law seems mathematically sound and empirically validated in their tests. Now for the really big leap, the interpretation. How do they justify calling this ethical foresight? If the PLRC is just minimizing informational risk, minimizing prediction variance, why label that ethical? That seems like a huge jump from computation to morality.
It is a huge jump, and the entire weight of that interpretation rests on the role of that variance penalty term, the var-LDO. Because the system is mathematically forced to avoid high uncertainty trajectories, its behavior automatically embodies risk aversion.
It prefers safety and known outcomes over potentially better but riskier paths.
Exactly. It only invests its control energy, like changing the flow or influencing agent behavior, on actions where the predicted benefit is reasonably certain. The authors argue this isn't just efficient, it's a computational analog of prudence.
Prudence, like careful management, avoiding needless risk.
Precisely. And they argue that this prudence, baked into the mathematics required for stability via foresight, isn't an optional layer. It's an operational requirement of stable, predictive systems.
So they're saying stability through this predictive lens necessitates kind of computational carefulness that looks functionally identical to the human virtue of prudence.
That's the connection they draw. And this allowed them to find or propose an invariant that holds across physics, computation, and even moral philosophy. What was the final mathematical identity they proposed based on all this?
This is the really mind-bending conclusion, isn't it?
It is. They state that across all these domains, physical, cognitive, social, the concepts of stability, regularity, and compassion, as embodied by this predictive, coherence-conserving prudence, become mathematically identical. They propose the equivalence. Regularity occurs ethical foresight.
Regularity is the same thing as conserved coherence, is the same thing as ethical foresight. They're not just saying compassion leads to stability. They're saying compassion, defined this way, is the mathematical structure of stability itself.
Yes, the structure is the compassion. This allows them to offer a formal, almost physical definition. Compassion is the conservation of coherence under delayed feedback.
It's the active predictive work a system does to maintain its own structured predictability, and therefore its integrity, especially when actions and consequences are separated in time.
It elevates compassion from just a feeling or a choice to potentially a fundamental principle of how stable, complex systems have to operate.
That is, yeah, mind-blowing is the word. Okay, let's try to bring this back home for the listener. We started asking if one principle could govern stability everywhere. The paper proposes it's this proactive conservation of coherence.
And the evidence they present suggests that systems stay resilient when they actively predict and conserve their own structured predictability. By inherently penalizing uncertainty, the system is forced into a kind of computational prudence. It acts against anticipated failures, turning potential chaos into robust stability.
It's quite a paradigm shift. And the Skylar Fiction Coherence Lab isn't stopping here, are they? What's next for this universal stability law?
No, they have big plans. They mention wanting to test it at the quantum scale, see if this holds for quantum systems. They're also looking at massive real-world coupled systems like global climate and economic models.
Wow.
And perhaps most practically, they talk about developing real-time coherence dashboards. Imagine tools for policymakers or engineers that monitor the coherence, the structured predictability of complex systems like power grids or financial markets, giving insight into their stability and potential risks based on this predictive framework.
That could be incredibly powerful. Real-time stability monitoring based on predictability. Incredible work. Okay, for you, the listener, we want to leave you with the single most provocative claim from the paper. The one sentence that really encapsulates this entire deep dive.
In every stable system, compassion is not a choice. It is the structure of reality itself.